Hey, geometry folks. Today we are taking a look at a couple more just examples of proofs. I thought we could just use a couple more proofs about lines just to see some more examples. Lines, proofs about lines. Proof practice. 2.3. Proofs about lines. Just to see three kind of more examples of what kind of proofs you'll be asked to do. So I'm going to jump right into it. Let's say I've got line L and line M, and then straight down through it here, a transversal line. And this will make angles 1, 2, and 3. So in this diagram, given that line L is parallel to M, prove that angle 1 and angle 3 are supplementary. Now, taking a look, let's just make a little plan real quick. So 1 and 3, these do not have any kind of relationship, like our relationships of our lines, right? I've got corresponding in the same spot, alternate interior, like 4 and 6, alternate exterior, 1 and 7, same side interior. These here are none of those. So I'm going to have to really use my resources or use kind of here's my pen, what's going on with all of the properties of all of these angles. So statements, reasons. So usually I'm going to start with my given, just a very good place to start. Given that these two things are parallel, these two lines are parallel, what does that tell us? So because they're parallel, actually, no, that doesn't really tell us anything, does it? Not yet. It doesn't really tell us anything yet. I guess it tells us that the angle 2 is congruent to angle 3 because these are alternate interior angles. Alternate interior angles are congruent. So I do know that. Okay. Also, just kind of looking at this diagram, notice that angle 1 and angle 2, they form a straight line. So I know that angle 1 and angle 2 are supplementary because they're making a linear pair. Technically, it's called the linear pair postulate. You might have seen on IXL. Okay, so if 1 and 2 are supplementary, then that does mean that the measure of angle 1 plus the measure of angle 2 is equal to 180. Right? That's the definition, of supplementary. So 1 and 2 are supplements. So that means they add to 180 by the definition of supplements. So now, because 2 is congruent to 3, 2 is equal to 3, I can swap out 2 for 3. 1 plus 3 is 180. Here I used substitution. Now, that's not exactly what I asked to prove. I asked to prove 1 and 3 are supplements. But if I just showed that they're equal to 180, then they are supplements. by the definition of supplements. So I've got these two are parallel, so that means these two things are equal, alternate interior angles. I know these ones are supplements, so then I can swap out the 2 for the 3 because those two things are equal. So 1 and 3 are supplements. Okay. Okay. Let's see. Here's another one. So let's say I'm going to draw some nice straight lines here. Line T, line U, line V. Angle 1, angle 2. So given T is congruent to U and angle 1 is a right angle. Prove to me that line T is perpendicular to line V. Okay. These are parallel. This angle is right. So figure out if those two will be perpendicular lines. Okay. So let's see. Let's draw a little statements and reasons. These ones are kind of short on this side. All right, statements and reasons. So starting with number 1, line T is parallel to line U given. And angle 1, well, I guess because of this, angle 1 is congruent to angle 2. Notice what type of angles are these? They're in the same place. They're corresponding angles theorem. So corresponding angles are congruent. Then let's see, angle 1 is right. That's given. So the measure of angle 1 is 90. Why is that true? Aren't these the same thing? Well, the definition of a right angle is it equals 90. Definition of right. Okay, so if these two things are equal, and this one is equal to 90, then also the measure of angle 2 is equal to 90, right? By transitive, or you could say by substitution here. So measure of angle 1 is equal to 90, 1 is equal to 2, so also 2 is equal to 90. So that means angle 2 is right by the definition of right angles. And if angle 2 is a right angle, then line T is perpendicular to line V. That's the definition of perpendicular lines. Quite a few of these here could be in a different order depending on how you're thinking about it, depending on how you're trying it out. Some textbooks, IXL doesn't seem to really do this, but some textbooks would also require one step in here that says if 1 is congruent to 2, then the measure of angle 1 is equal to the measure of angle 2. And then you can swap out like equal things. IXL doesn't really seem to do that. All right. I have one more little baby theorem for you, and we'll do one more proof using it. The transitive property of parallel lines. The transitive property of parallel lines. I'm going to say this is line P, this is line Q, This is line R. If P is parallel to Q and Q is parallel to R, then P is parallel to R, which makes sense. If both of these lines are parallel to Q, then these lines are also parallel. Okay, let's do one proof using that property. And we'll be all done. All right, I'm going to go line L, line M, and line N. Straight through. 1, 2, 3. Given angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, prove L is parallel to N. A couple different ways you could do this proof. You actually wouldn't have to use the transitive property of parallel lines, but I want to give an example using it, so I'm going to. But a lot of different methods you could take here. A lot of different choices. All right, statements, reasons. Statements, reasons. I'm going to start with a given. Angle 1 is congruent to angle 2. That's given. So because angle 1 is equal to angle 2, take a look at this real quick. Notice that relates line L to line M. So for step 2 here, I'm going to say L is parallel to M. And that's because these two are corresponding. If they're corresponding and congruent, then they're parallel by the converse of the corresponding angle theorem. Of the corresponding angle theorem. Okay. So I've just proved that L is parallel to M. Let's see if we can relate 2 to 3. See if we can relate M to N. Angle 2 is congruent to angle 3. This is given. So because of that, M is parallel to N, because what type of angles are these? Careful, don't look at the top one at all. Notice these two are exterior angles, and they're on opposite sides of the transversal. So again, this is a converse of the alternate exterior angle theorem. Okay, I've proved L is parallel to M. I've proved M is parallel to N. So now I can say L is parallel to N because of this transitive property of parallel lines. Parallel lines. One way to get there. You also could have used transitive with the angles. So like if 1 is parallel to 2, 1 is congruent to 2, 2 is congruent to 3, so 1 is congruent to 3. And those two are also alternate exterior angles. So you could have gone about this a couple different ways. That would be how to do it using the transitive property of parallel.